Chapter 1, Installation Guide. One of the books that you received in your handout materials is the installation guide for closed-loop ground source heat pumps. And in this installation guide, we have a number of materials that are important, and a number of topics that we'd like to cover that is important as we get along in the CGD material. As I said, the reference material is a closed-loop ground source heat pump systems installation guide, and this is a cooperative project with the National Rural Electric Cooperative Association, Oklahoma State University, and the International Ground Source Heat Pump Association. All three of these were participants in the development of this guide, as well as an industrial advisory board that did a peer review on this thing to make sure that it did fit what was needed in the industry. Now, in our introduction, we talked about the source of energy being the sun. It's energy being stored in the surface of the ground, where we said about 46% of that energy is stored in the ground. And that energy is what we want to then pick up with our ground source heat pump system and bring up into our building load, or taking energy during the cooling load and put that back into the ground. Now, the temperatures that we have underground and the temperatures that we have in the air, we want to take a look at both of those so that you see what is the advantage of the ground. The ground will be, as we will show, will be a more stable environment temperature-wise. Our first slide is a picture or a representation of the average air temperatures that we have in Stillwater, Oklahoma. Now, this same kind of information that we have is also available for a large number of sites around the United States as well as around the world. In this particular reference we have down here, the data source is Air Force Manual 8829, which is now probably a better source of information is NOAA, National Oceanic and Atmospheric Administration. You can get from them a data disk, and it has all the different kinds of information as far as the air temperatures at any one location. It will be necessary, as you will see in further lessons, to have this information, because when we start taking a look to calculate building loads, we need to know what the outdoor air temperatures are, and also when we're going to be looking at the annual operating costs. Now, for Stillwater, Oklahoma, we have a number of things that are available and a number of things that we'll be using. I've labeled point A up there at the top as extreme condition, and at the top up there you can see that at the extreme condition in the summer we're at a temperature of about 100-105 degrees Fahrenheit. If we go down to the bottom of the page, the extreme temperature in January, or the extreme temperature, not necessarily just in January, but whenever the extreme temperature does occur, it's below zero. So you can see that the air temperature extremes range about plus or minus 50 degrees for this location, and that represents a pretty big swing. In air source heat pumps or equipment that uses outdoor air temperatures or fresh air, these are the temperatures that you might expect. Now, from a design standpoint, because those temperatures just occur rarely in the summer and also in the winter, we have what we call summer design conditions and winter design conditions, and they're defined by the summer design condition ASHRAE 2.5, and that says now the average, not the average temperature, but only 2.5% of the time will the temperatures be above this design condition. In this case here, it looks like that's about 92 or 93 degrees Fahrenheit. In the wintertime, it looks like the temperature might be down at an hour or so in Stillwater, Oklahoma, maybe a minus 5 degrees Fahrenheit. But 97.5% of the time, it will be warmer than about 10 or 12 degrees Fahrenheit. So then that becomes the winter design condition. Plotted on the curve right here is the annual average temperature by month. And you can see in January, if you just looked at the average temperature in January, that it looks like it's around 34, 35 degrees Fahrenheit. In July and August, in July or August, it looks like it's up around, just the average for the whole month is around 92. But it can get up to as high as 105. So you have a plot here of the average annual air temperatures, but the daily or the hourly temperature just jumps all over the place, and so the average temperatures are here nice to look at, but they don't represent exactly what's happening on an hourly or daily basis. Across the middle there you see a horizontal line. We say that's the annual average temperature of the air in Stillwater, Oklahoma, which says that's a nice balmy 59 to 62 degrees Fahrenheit. So if you lived in Stillwater, you might say, well, on the average, it's a really pretty nice place to live. In August, it can get up to 105. In January, it can get down as low as a -10. But on the average, you know, it's a pretty nice place to be. So we have the extreme condition in the summer, the extreme condition in the winter. But more importantly than these extreme conditions are the summer design temperatures and the winter design temperature. So this is just a little information about what the air temperatures. And I guess you could probably assume at this point here is that what we're doing is getting you set up to look at what the ground temperature is going to be like, because it's obviously going to be better. Assume at this point here is that the sun shining on the surface of the earth, that thermal energy has to penetrate into the ground, and it is dampened. The large swings are dampened as you go underground. Now, this is the annual soil temperature variation. What you saw previously was the annual air temperature variation. Now, the soil temperature is much more moderate. You can see that at the ground surface, the one curve there, the one that has the largest amplitude, you can see that it goes down and it looks like it hits a low of about 38 degrees Fahrenheit, goes up to about a high of about 82 or 83. Now we call that the ground surface. The ground surface is not a thermocouple or a measuring device laying at the surface of the earth, but it's a couple inches below the top of the ground, because originally most of the soil temperature data that was recorded was for farmers, so that they had some idea of when the soil temperature was appropriate for planting. And so when we talk about the ground surface temperature, we're going to be talking about somewhere around 2 to 3 inches below the ground surface. Now, in order to describe these curves, you can see they're sinusoidal, or they go up and they go down, and we would call that sinusoidal. Our representation is sinusoidal. You can see that we have 2 points that we've labeled in red. One of them is A sub S. That's the annual swing. Okay, you can see from the mean temperature here that we have is 62 degrees. Remember, we said the annual average air temperature was about 52. The average annual ground temperature, if we go down far enough into the surface of the earth, like say 40, 50 feet, it remains constant at about 62 degrees Fahrenheit. That's about 2 or 3 degrees warmer than the annual air temperature, and that's because the crust of the earth acts as kind of an insulator. As the soil dries at the surface of the earth, that slows down the heat transfer, and so that's why you find the ground temperature just a couple of degrees warmer than the average annual air temperature. Now we define that curve in 2 ways. The amplitude, how it ranges above and below that 62 degrees Fahrenheit. And you can see that at the surface it looks like it goes up there 20 or 30 degrees. Above that in the summertime, it goes below that in the wintertime. The other curve, or the other data or defining point that we have on here is the phase shift, T sub 0. And that's the number of days from January the 1st before the amplitude at the surface reaches its minimum. So you can see that we're talking around, the phase shift is around 35, 36 degree, 35, 36 days after January the 1st. So that means that there is a delay. January 1st is not necessarily the coldest day, but soil temperature wise, it is delayed from January the 1st by about 8 degrees, or 38 days. The amplitude is in degrees.